Yes, so welcome everyone to the Good Vibration Seminars for the third season. This morning we're very happy to welcome Raffaele Reda for our third episode of the third season. We have Savita Mathur here with us to introduce Raffaele. Thank you, Savita, for having accepted.
Okay, so yeah, today it's my pleasure to introduce Raffaele Reda for the Good Vibration Seminar. So let me talk a little bit about what he did in the past. So he actually did his bachelor's and master's degrees in physics at the University of Calabria in Italy, mostly on climate models, so very different topic than what he's doing, well, a little bit different from what he's doing now. And he did his master's degree on a model of Earth's climate sensitivity to solar irradiance variations with Professor Fabio Lipreti and Leonardo Primavera and Antonio Vecchio. And so that was in 2019. And then he started his PhD in astronomy and astrophysics and space science at the University of Rome, and also in collaboration with INAF. And his thesis is about a synergic strategy to characterize the habitability conditions of exoplanets hosted by solar type stars. So the talk we will listen to. And he's supervised by Dr. Luca Giovanelli and co-supervised by Maria Pia and Francesco Birilli. So I think Raffaele already has 3 papers. Well, one was just recently accepted on exactly on the conditions of habitability of exoplanets. So I think we will hear more about this. And he's currently finishing writing his PhD, his thesis, and should defend sometime early next year. So I think that's all I had to say. So the floor is yours.
Okay. Can you see the presentation?
Yes.
Okay. Hi, everyone, and thank you, Savita, for your kind introduction. Let me thanks also the organizer of this seminar series in order to give me the opportunity to give this talk today. During this presentation, I will show you some of the results achieved within my PhD thesis project, whose title is a synergic strategy to characterize the habitability condition of exoplanets hosted by solar-type stars. Let me stress the fact that I'm not an astroseismologist, but during this presentation, I would like to point out some of the possible connection between astroseismology and exoplanets. In particular, the way in which astroseismology can support the characterization of exoplanets' habitability. The exoplanets research field is a quite young research field. Indeed, the first detection of an extrasolar planet was reported only 27 years ago, in 1995, by Major Achilles, who detected the presence of a Jupiter mass companion to a solar-type star. After this detection, the interest in the exoplanets research field grows enormously, and with it also the number of detected extrasolar planets, at the point that 27 years later, we have more than 5,000 confirmed extrasolar planets and thousands of candidate objects. In this respect, one of the most fascinating challenges is to find planets with conditions suitable to host life, so habitable planets. Many times the concept of habitability is related to the concept of habitable zone, which is defined as the range of distances from the host star where a terrestrial-like planet would potentially maintain liquid water on its surface. This definition depends, as you can see on the scheme here, from the distance of the orbiting planet from the host star, but also on the stellar type, here expressed in terms of mass. But this definition of habitability is based only on the energy balance between the incoming stellar energy and the outcoming planetary radiation, and so it is only a Rayleigh approximation of habitability. A great example in this sense is provided by the TRAPPIST-1 planetary system. For this planetary system in 2017, Yole et al. Announced the discovery of 7 terrestrial-like planets, with 3 of them in the habitable zone. Now the question is, are those 3 planets in the habitable zone habitable? Many authors investigated the effect of this of the stellar activity on these planets, and what they found is that all the planets in the TRAPPIST-1 planetary system experience a very strong stellar wind pressure of the order of 10 to the 3, 10 to the 5 times that of the solar wind on Earth, and so they conclude that probably all the planets in the TRAPPIST-1 planetary systems no longer have an atmosphere. So what you have to take in mind is that for a planet, be in the habitable zone is not enough to be habitable. Indeed, an in-depth characterization of the habitability condition of exoplanets need at least 3 main ingredients. The first one is a planetary characterization, which means to know the bulk property of the planet, like the mass and the radius, but also the orbiting distance from the host star, so on the semi-major axis. Then we need information about the equilibrium temperature of the planet, which depends on the atmospheric composition of the planet, so we need also an atmospheric characterization. And finally, from this side, we need also to have information about the possible presence of a planetary magnetic field, which play a fundamental role in the habitability condition of a planet, as we will see later. Then we need also a stellar characterization, which means to have precise determination of the mass and the radius of the star, as well as the rotational period. But we need also a precise information about the age of the star, as well as about the activity level of the star. And finally, we have to study the way in which the host star interact with the environment around it, in particular with the orbiting planet. So we have to study the so-called space weather phenomena. We have to take into account the flaring activity, and we need also to assess the way in which the stellar wind interact with the orbiting planet, in particular with the planetary magnetic field. My PhD thesis project aimed to, from one side, characterize sun-like stars, and on the other side, determine and study the way in which the stellar activity can impact on the planetary habitability. But why it's so important to study the way in which the stellar activity impact on the planet? This is because many of the processes that impact the habitability of an exoplanet or a planet in general came exactly from the interaction between the phenomena related to stellar activity in different forms, like flares, stellar wind, or coronal mass ejection, and the orbiting planet. In this respect, we can distinguish between 2 main classes of event. Event called transient event, which are events with typical time scale smaller compared to the rotational period of the star, which are studied by space weather. And then we have stationary phenomena, which are phenomena with typical time scales larger compared to the rotational period of the star, which are studied by space climate. When we study the effect of stellar activity related phenomena on an orbiting planet, we have to take in mind that the presence of a planetary magnetic field usually shield the underlying planetary atmosphere from being eroded by the effect of the stellar activity. An example of stationary phenomena is the stellar wind, which is a continuous flow of high-energetic particles coming from the outer atmospheric layer of a star, which is the corona. The stellar wind strongly interact with the environment around the planet, in particular with the planetary magnetic field, compressing and perturbing it. And if the wind is too strong, and if the protection provided by the planetary magnetic field is not enough, we can have a direct impact of the solar wind particle on the planetary atmosphere, which can also be maybe eroded. Starting from MHD equation and assuming a stationary equilibrium, as shown here, we have that the balance between the solar wind dynamic pressure, this term here, with the pressure of the planetary magnetic field establish the compression of the of a planetary magnetosphere. In this case, expressed here in terms of RMP, where RMP is the so-called magnetopause of distance. And as you can see on the formula, this distance depends on ME, where ME is the planetary magnetic moment, but also on P, where P is the dynamic pressure of the wind. So an assessment of the stellar wind pressure is of paramount importance from the habitability point of view. Here there is a visualization of the effect of the stellar wind dynamic pressure more in general, but in this case of the solar wind dynamic pressure on the Earth. In particular, these results are from simulation coming from the work by Raffaele et al. Of 2022. On the picture on the left, you can see an average situation corresponding to a dynamic pressure of 1.2 nanopascal, which is the average value of the solar wind dynamic pressure along a solar cycle. While on the other side, on the right picture, you can see an extreme situation corresponding in this case to a value of the solar wind dynamic pressure of 30 nanopascal. Which result in a very compressed Earth magnetosphere, as you can see here. But if we have a strong solar wind dynamic pressure, we have also a very high density of solar wind particle here near the Earth, and those particles can strongly interact with the particle of the Earth atmosphere. So, as I said, one of the results of the interaction between solar wind and the Earth's magnetic field is the shape of the planetary, in this case of the Earth magnetosphere, which is the region of space here that you can see in blue. And within this region, the particle motion is dominated by the planetary magnetic field, while on the other side, on this side, we have that the particle motion is dominated by the solar wind. This interaction in the Sun-Earth system results in a compression on the Earth side of the magnetosphere up to a distance around 11 Earth-radi. But we know that this extension was smaller, for example, around 5 Earth-radi when the Sun was younger and more active. Indeed, the extension of the magnetosphere of terrestrial-like planet typically depends, as we can see on the scheme here by C et al., both on the chromospheric activity of the star and on the stellar type, here expressed in terms of stellar mass. But since the solar system is the only planetary system that we can study and observe in detail, the connection between the solar activity and the solar wind have to constitute a starting point for any other study of this type on other stars. This is the reason why, as a first step within my PhD, I studied the long-term relation between solar activity and solar wind properties. To do that, the first thing to do is to quantify the solar activity. This can be done in different ways and by using different indices. In this respect, we can distinguish between synthetic indices, like the famous sunspot number. But I think that the best way to quantify the solar activity is by using physical indices, which are indices directly related to a physical observable, for example, like the flux in a particular band. In this respect, for this work, we used the calcium 2K index, which is, as I said, a physical index, in particular connected to the mean emission of the solar chromosphere. For this index, we have direct measurements within the coming from the National Solar Observatory website, starting from February 97 up to October 2017, but we further extend this data set up to April 2021 by using another physical index of the solar activity, like the magnesium 2 index. For the solar wind, for the reason that I mentioned before, we looked at with particular attention to the speed and the dynamic pressure, for which within the Omni database, we have direct measurements starting from July 1965 up to April 2021. The Omni database is a NASA database where all the measurements of solar wind parameters coming from different spacecraft are collected. So with our analysis, we have an overlapping time interval of the dataset going from July 1965 up to April 2021. So we are able to cover almost entirely the last 5 solar cycles. Here on the left, you can see the 3 signals used for this work, in particular in green, the calcium 2K index, in red, the solar wind speed, and in blue, the solar wind dynamic pressure, with the superimposed 37-month moving average that we used in order to study the long-term behavior of these signals. As a first step, we studied the simple correlation between the signal, but what we found is that there is no simple correlation between calcium 2K index and both solar wind speed and dynamic pressure. And then we asked ourselves about a possible delayed response of the solar wind parameter with respect to the solar activity. In order to infer a possible time delay between the signal, we computed a cross-correlation analysis, whose results are shown here, in particular on the panel A for the pair calcium 2K index and solar wind speed, and the panel C for the pair calcium 2K index, solar wind dynamic pressure. But in order to take into account also a possible nonlinear relation between the parameters, we computed a mutual information analysis with the result here. But what we found is that the lag coming from the 2 different approaches are consistent between them. And in particular, we found a mean 3.2 year lag of the solar wind speed with respect to the calcium 2K index, while the lag became 3.6 years when we instead looked to the dynamic pressure. These results are in agreement with the result of previous work, but the difference is that all the previous work estimated the solar activity by using a synthetic index like as the sunspot number, but for this work we used, as I said before, a physical index. By taking into account the lag with the previous analysis, we found a positive correlation of both the calcium 2K index with both the solar wind speed as shown in the scatter plot here on the left, but also with the solar wind dynamic pressure as shown here on the scatter plot on the right. In particular, of great interest is the relation found between the calcium 2K index and the solar wind dynamic pressure, because as you can remember from what I said before, the solar wind dynamic pressure play a very important role in the compression of the Earth magnetosphere. So once we have a relation between the solar wind dynamic pressure and the calcium 2K index, we can take it, we can put it in the formula of RMP, and we are now able to directly estimate the extension of the Earth magnetosphere, simply starting from the emission of the sun in the K line of the calcium 2. Now, the advantage of having used for this work a physical index of the solar activity like the calcium 2K index is that now the relation found for the sun can be easily extended to stars different from the sun, in particular to sun-like stars. So mainly to G spectral type star with a mass in the range between 0.9 and 1.1 solar masses, with a radius around 1 solar radii, with a photospheric temperature in the range between 5,000 and 6,000 Kelvin. But as a further constraint, we have also to look at the activity regime of the star, which has to be similar to the solar one. So as you can understand, in order to apply our procedure to stars different from the sun, we really need to characterize those stars. And this can be, for example, done by using asteroseismology. In order to extend our model to stars different from the sun, we need measurements for those stars in the calcium 2H and K line. During the time, many observational campaigns for the emission in the calcium 2H and K line for sun-like star was performed. In particular, the widest one was the one performed at the Mount Wilson Observatory between 1966 and 1995, then continued at the Lowell Observatory. But there are still ongoing observational campaign for the emission in the calcium 2H and K line, like the one performed at the Tigre telescope. The measurements from this observational campaign are expressed in terms of a syntax, which is an adimensional index, based on the emission of a star in the H and K line normalized to the continuum. And thanks to the work by Hegel and et al. Of 2017, we have a relation which allows us to directly go from the S index to the calcium 2K index and vice versa. Now the question is, how do we select the stars to which we extend our model? One way is by using the Rossby number, which is defined as the ratio between the rotational period of the star and tau, where tau is the convective turnover time of the star. In this respect, we have, as I said before, to look at the activity regime of the star, which depends on the photospheric and chromospheric variability of the star. In this respect, we can have a star for which the photospheric variability is in antiphase compared to the chromospheric one. This is the case of the younger star, which are called spot dominated. And then we have star like the sun, for which we have that the photospheric variability is in phase with the chromospheric one, and these stars are called facula dominated. The very interesting thing is that in 2019, Reynolds et al. Found that the transition from one activity regime to the other, so from spot dominated to facula dominated, seemed to occur at a Rossby number around 1, which corresponds to a stellar age around 2.5 to 2.6 giga-year. So by using the prescription by Reynolds et al., we selected a sample of sun-like star starting from the Rossby number. And starting from the emission of those stars in the calcium 2, H, and K line from the Mount Wilson Observatory, we studied the magnetospheric extension of fictitious Earth-twin planets orbiting at 1 astronomical unit around those stars. Here on the table, you can see the list of the stars, of this sample of stars and their main properties. In particular, in the column with the box, you can see the result from our model for the magnetopost and of distance, so from the extension of the planetary magnetosphere. And on the right, you can see a comparison with the result from the same stars by a previous work, in particular by C et al. Of 2014, where the solar wind properties have been estimated in a more sophisticated way compared to our model, in particular in this case by using the Parker solar wind model. But as you can see, within the confidence interval, the results from our work are in agreement with the ones by C et al. So what we can say is that our model seems to work good. So once we have calibrated our model and we know that our model works, we are now able to apply this procedure in combination with other approach. For example, as I said before, in combination with asteroseismology. Trying to do this, we faced a very interesting stellar case, which is the case of Gliese 504, which is a solar-like star. But at the same time, this stellar attack was an unfortunate case, as I will show you in the next slides. This is a very intriguing case because in 2013, Kuzuera et al. Identified a Jovinian planet orbiting this star. But up to now, the exact nature of this planet is not clear. Indeed, the planet could be a Jovinian planet or a brown dwarf. The reason for that is because the planet has been detected by using direct imaging, and so we do not have radial velocity measurements for this star. And so the mass of the orbiting planet needs to be estimated in other ways. In particular, in this case, the way is by compare the observed planet luminosity in each band with the luminosity coming from theoretical models, but theoretical models need as input the stellar age. So as you can understand, in this case, the nature of the planets depend on the star age. During the time, different authors tried to characterize this star. with controversial result. In particular, some authors pointed out a very young stellar age for this star of the order of few million years, but the other authors indicate a solar-like age of the order of 4, for example, giga-year. And according to the different age estimation, we have a different nature of the orbiting planet of Gliese 504. And so the evolutionary stage and the age of this star are still an open question. In order to try to make light on the age of this star and also on the nature of its companion, we decided to use an astereoseismic approach. In this respect, as a first step, by using the relation by Kilson embedding, we tried to estimate the range of frequency where we expect a power excess for this star. In particular, by starting from the effective temperature and the surface gravity coming from different work, we estimated the expected value of the Numax for this star. Obviously, we have different value according to the different input parameter, but with the exception of the value coming from the parameter by Valenti et Fischer, we expect for this star to found a power excess, a theoretical power excess in the frequency range between 1.8 and 2.3 millihertz. This work was conducted within the task, which is the Test Asteroseismic Science Consortium. Here you can see the list of all the authors of this work, which I would like to thank once again. This star was observed by test during sector 23 in 2 minutes cadence mode, and during sector 15 during sector 50 in 20-second cadence mode. Here you can see the power spectral density of the star, in particular within the red box, the region of frequency where we expected for the star to found a power excess. The light curve were analyzed by different groups and by using a large number of techniques and tools here listed, but we were not able to find an evidence of clear power excess for this star. Now the question is, what's the reason for the non-detection? In order to answer to this question, we studied the magnetic activity of this star, in particular starting from the Mount Wilson observation available for this star for the time period going from 1966 up to 1995. Here on the panel on the top left, you can see the S-index measurements for this star. And in particular, from these measurements, we found that this star should have a periodic cycle of with a mean length around 12 years. But we found also the presence of smaller timescale cycles, as for example this one and this 1 year. But the very interesting thing is that this star is characterized by a very high magnetic activity level corresponding to an S-index of 0.313, which is around 2 times that of the Sun. Then, by using this value of the S-index and by taking advantage of the formula by Bonan et al., in which from which we can obtain the maximum expected global oscillation amplitude starting from the S-index, we expected for this star a global oscillation amplitude of 1.6 parts per million, which is a very low value if compared to the level of noise on the data of this star. And so the magnetic activity justified the suppression of star-like oscillation for this star as already found in other targets. Even with no oscillation detection, we were able to constrain the fundamental stellar parameter of Gliese 504, in particular by using information coming from observational spectroscopic constraints. coming from stellar evolutionary model, but also coming from the analysis on the magnetic activity of the star. On the plot on the left, you can see some theoretical models obtained by using the Aztec evolutionary code, and where we changed the mass and the composition of the star in order to match the observational spectroscopic parameter of the star, in particular the effective temperature and the surface gravity. By using this all the theoretical model matching this spectroscopic constraint, we here on the table summarize the main property of the star. In particular, we found a mass which has to be around 1.2, 1.3 solar masses, with a radius value of around 1.38 solar radii. But the most interesting parameter is the age of the star, for which we estimate an age of 1.3 plus minus 1.3 giga-year. And this result is also in agreement with the information coming from the magnetic activity analysis on the star, from which we know that the star is still in the spot-dominated activity regime, which means that the star has to be younger than the sun. Then, in order to try to predict the observed pulsation scenario for the star, we used the IAPS package in order to compute the theoretical adiabatic oscillation frequency for the star. In particular, from the theoretical model that I showed you before, we found a theoretical expected value for the large separation frequency of 98 plus minus 13 microhertz. And here on the plot on the left, you can see two of the extreme model of the previous slide. In particular, with the extreme model, I mean the one with the lowest mass and the one with the highest mass. And here you can see the expected theoretical large separation frequency for these two models. In particular, the one with the black color, for which we have a large separation frequency around 105 microhertz, and the one in blue, for which we have a value of the large separation frequencies around 86, 87 microhertz. And this is very interesting to note that this model, which corresponds to a stellar age of around 2.5 giga-years, seem to be compatible with the unconfirmed value of the large frequency separation for the star, which is a value which is measured on the data, but with a non-significant statistical level. On the right panel, instead, you can see the so-called shell diagram for the two models. But as you can understand from the plot on the left, even just the value of the large separation frequency when measured for the star will definitely help to constrain the debated evolutionary stage of the star, and so also the nature of its companion. Going to the conclusion, we summarized our synergic strategy to characterize the habitability condition of exoplanet hosted by solar type star in a paper, in a perspective paper published on Frontiers, in which we underlined all the possible connection between asteroseismology from one side and another type of approach, in particular a space climate approach, as I show you during this presentation on the other side. In particular, we know that with asteroseismology, we can obtain a precise stellar characterization. We can also study the evolution of the magnetic activity of a star, simply looking at the evolution of the oscillation parameter of a star, but we also have an impact of the magnetic activity of the star on the characterization on the stellar characterization, as in the case of Gliese 504. On the other side, For example, we can estimate the value of a planetary magnetic field intensity starting from a dynamo model and assuming an internal structure model. And once we have the value of the planetary magnetic field intensity, we can take it and we can put it in our sun-calibrated model. And we are in this sense, able to estimate the mean stellar wind speed, the mean stellar wind dynamic pressure, and as well as the extension of a planetary magnetic field, simply starting from the emission of the O star in the calcium 2 H and K lines. We believe that this strategy could be of relevance in the context of both present and future space mission. In particular, the data coming from Kepler and TESS could be very helpful in the characterization from the astroseismology point of view of the O star, but also the data coming from the James Webb Space Telescope, from which we can have, for example, direct imaging detection, as in the case of Gliese 504. But probably the most interesting space mission will be the Plato 1, which will be launched in 2026. Indeed, the primary target of this mission will be the detection of terrestrial exoplanets in the habitable zone around Sun-like star, which are exactly the best target on which to apply our Synergic strategy. Of relevance could be also the data provided by Gaia, in particular the data by the data release 3 of Gaia, from which we have stellar activity measurements in the calcium 2 triplet for an enormous number of stars of the order of 1 million. So in the next months, we plan to extend our Synergic strategy to a large sample of solar type stars. In this respect, we have already selected around 50 stars for which we have both asteroseismic observation by test in 2 minutes cadent mode or in 20-second cadent mode. But for this star, we have also measurements in the calcium 2 H and K lines coming from the Mount Wilson Observatory. Here on the table on the left, you can see the name of the selected stellar target. If you have already studied some of this stellar target, or if you are interested in help us in study from the astroseismology point of view those stars, or if you have any other idea to improve our Synergic strategy, we are open to collaboration. If you have any question, or if you want to collaborate with us, you can write me. I leave here my contact, my mail, and that's all from me. And thank you for your attention.
Thank you very much, Raffaele. Let me upload for everyone that's here, and you can use the icon of the Zoom. Yeah, that was very interesting, and I'm happy to see that. That was actually one of my concerns, that whenever you talk about habitable zone, and if they are really habitable given the magnetic activity of the host stars. So that's very nice that you're looking into this. Yeah, we have time for questions. So I don't know if anyone wants to ask a question. You can raise your hand or ask the question in the chat. I don't see anyone. So maybe I will go ahead with one of my question. So you started to look at solar-like stars G and K dwarfs. I was wondering if you were also interested in looking at M dwarfs, which are also like one of the targets for the TESS mission, and which also are known to have a lot of flares, which you didn't really mention, and that can also maybe impact the development of life on the planets.
Okay, thank you, Sarita. This is a very interesting question. For the moment, we plan to apply our strategy only to stars quite similar to the Sun, since the model that I calibrated, the relation that I calibrated on the Sun in order to estimate the stellar wind parameter, as I said, has been calibrated on the Sun. So we don't know if these things work in a different way for other type of star. In particular, we know that M dwarf are a very complicated star. I don't know if this procedure can be applied also to M dwarf, but probably they constitute a very intriguing stellar target, since many of the detected terrestrial-like planets have been detected orbiting around M dwarf. But we hope in the next future with the Plato mission, as I said, to have also terrestrial-like to detect also terrestrial-like planets orbiting around star-like stars.
Okay. Okay. Still don't see anyone raising their hand. So actually, you can maybe stay on this slide. I was curious about. So you were mentioning this lag between the SMHK and the wind speed and pressure. I was wondering, is that so? You said that it was already shown by other works using sunspot number, but what about the theory? Was it the time lag expected from theoretical models? I don't know if that has been studied for the wind. Yeah.
This is another interesting question. When we performed this analysis, we do not know anything about the possible presence of time lag of the solar wind parameter with respect to the activity of the sun. But then we read some paper and we found that this was unknown things. And there are some theoretical models. In particular, there is a paper published last year by Perry et al., in which they used a three-dimensional MHD model in order to modeling the stellar wind, in particular in the case of a very young sun. And what they found is that there is a sort of coupling between the magnetic activity of the star and the wind, which can result in during a longer cycle in a sort of time lag. But this model has been, the simulation for this case has been performed, as I said, only for a very young star, but we don't know if the things work in the same way for the sun, but probably yes.
Okay, thanks. Anyone else with questions? Don't be shy. I don't think I see anything on the chat. Oh, Masao, yes, go ahead.
Okay. Okay, thank you very much for nice talk. I'm not familiar with the subject, so my question is quite naive. You said that magnetic field of planets are also important to discuss habitability, right?
Yes.
I'm wondering whether it is possible to get information of planet magnetic field observationally.
Okay, this is not a simple. This is not a simple task, but I know that during in the literature there are some authors that propose method for detecting the intensity of exoplanets' magnetic field. I exactly don't remember the way, but for example, one way could be by looking at the bow shock of the planet during the transit of the planet in front of the star. But we don't know if this type of method work. Probably the best method in order to infer the intensity of the magnetic field is by using a theoretical model where you, as I said, can assume an internal structure for the planets once you have.
Well, but in this case, we have to understand dynamic process in the core of the planet. Is that right?
Yes.
Okay. I'm not sure how, say, reliable those theories are currently.
Sorry, can you repeat?
Okay. I am not sure whether we have very good reliable theory about planetary, say, dynamic process or not.
Okay, I'm not an expert on this field, but So I don't know if the dynamo model that we have for the internal structure of the Earth works, but we probably have to ask to someone which works in this field.
Yeah. Okay. Thank you very much.
Okay. Any other questions? I don't think I see. Yeah, I don't see anyone else. So maybe we can stop here then. Thank you again, Raffaele, for this very interesting and great talk.
Thank you for inviting me.
And we wish you best of luck for finishing your thesis and your defense. And yeah, I don't know if Rita, you wanted to say something.
Thank you very much, Savita, also for chairing this seminar. Thank you again, Raffaele. And I think we meet again in 2 weeks to listen to Yagwang Lee from University of Sydney, who will talk about using solar-like oscillations to characterize main sequence and red giant stars. Thanks again, everyone, and see you next time. Bye-bye.
Thank you. Bye.
Bye-bye. Thank you.
Bye.